Guys, welcome to today's video. We are going to be looking at the relevant Laplace transforms that you need to know in solving ordinary differential equations. Okay, so Laplace transforms is a broad topic on its own. We use Laplace transform for frequency domain analysis, but for the purpose of this course in ordinary differential equations, I'm just going to show you the relevant ones that you need to know, of course, when you need to solve ordinary differential equations. So first of all, I'll start with the definition of Laplace transforms for a particular function in time domain. So just know that, sorry about that, what you need to know formally is that Laplace transforms converts functions in from time domain, that's t, to frequency domain, and the frequency domain is using the s variable. So the definition is that the Laplace transform of a function of time f of t is given to us as the integral from 0 to infinity. So we have exponential minus st multiplied by f of t, and we are integrating with respect to t, and this is going to give me particular capital F of s. Okay, so when we perform this integral, we are going to get a function in terms of f of s. So the summary is that f of t and f of s form a Laplace transform pair. Okay, form a Laplace transform pair. Laplace transform pair. So it means that when you take the Laplace transform of f of t, you're going to get capital letter F of s, and when you take the inverse Laplace transform of f of s, you're going to get f of t. Okay, so the Laplace transform pair, I repeat again, when you take the Laplace transform of f of t, you're going to get f of s. Then when you take the inverse Laplace transform of f of s, you get f of t. So this is an introduction to what Laplace transform is. So we're going to be looking at the Laplace transform of some common functions that you should know. Okay, so Laplace transform of some common functions. Okay, that you should know. Now, the Laplace transform of these functions, they are not going to be derived in this particular lessons. I'm not going to derive them in these lessons. I'm just going to write their forms so that you will know how to obtain them. Okay, so in future videos, I am trusting that we will derive them. I'm going to prepare a whole topic or a whole course on Laplace transforms for those of us that want to know the intricacies of Laplace transforms. But for now, I'm going to start with some common functions. Now, the Laplace transform of 1 is 1 over s. Okay, and 1 is actually corresponding to the unit step function. Okay, so the Laplace transform of 1 is 1 over s, or the Laplace transform of u of t is 1 over s. The Laplace transform of t is actually 1 over s squared. Okay, so take note of this. The Laplace transform of t is 1 over s squared. The Laplace transform of t raised to the power of n can be written as n factorial over s raised to the power of n plus 1. Okay, so this is the general formula for the Laplace transform for n t raised to the power n, where n is greater than 0. Okay, n is greater than 0 in this case, or n is greater than or equal to 0, if I'll put it like that. So this is for, let me say, polynomials. Okay, Laplace transform of 1t and t raised to the power of n. So let's go to exponentials now. So these are polynomials. So let's go to exponentials now. So for exponentials, the Laplace transform of exponential at is going to be 1 over s minus a. Okay, the Laplace transform of exponential at is 1 over s minus a. The Laplace transform of exponential negative at is going to be 1 over s plus a. Okay, so you're going to find it useful because maybe when we use partial fractions to separate some particular problems and we get 1 over s minus a and we want to take the inverse Laplace transform, then we'll now end at this exponential form. Is that okay? But just take note that this is the Laplace transform for exponentials. So these two are very important, and together they summarize the Laplace transform for exponentials. So finally, I'm going to show us the Laplace transform for trigonometrics, and this is the only one that I'm going to do some little calculations so that you will understand how we actually came about it. Now the Laplace transform for trigonometric, okay, so the Laplace transform for trigonometric, the Laplace transform for trigonometric forms, we have the Laplace transform for sine AC. So the Laplace transform for sine at is a over s square plus a square. So this is the Laplace transform for sine at. The Laplace transform for cos at is actually s over s square plus a square. Okay, so someone will be wondering, how did we get the Laplace transform for sine at and the Laplace transform for cos at? So quickly, you just have to remember Euler's identities. Recall Euler's identity. Euler's identities teaches us to express the sine and the cosine functions as exponential, okay, or complex exponential functions. So when you convert sine at to a complex exponential, sine at can be converted to a complex exponential in this form: exponential j at minus exponential minus j at over 2j. Is that okay? And the same thing happens to cos at. It can be expressed as exponential j at plus exponential minus j at over 2. So these are the complex representations of sine at and cos at. So if you want to take the Laplace transform of sine at, for instance, the Laplace transform of sine at is actually corresponding to the Laplace transform of exponential j at minus exponential minus j at over 2j. Okay, and since j is a constant, of course j is our imaginary number, and this 2j is also a constant, so we can actually remove it from the brackets just like we normally remove constants of integration. So we have 1 over 2j Laplace transform of exponential j at minus exponential minus j at. Is that okay? So if you are still on this, the Laplace transform of sine at is equal to 1 over 2j. Then we're now going to take the Laplace transform of exponential j at and exponential minus j at. So remember, j is a constant, a is a constant, so t is the independent variable. And remember that when you're taking the Laplace transform of exponential at, you're going to get what? 1 over s minus a. When you take the Laplace transform of exponential minus at, you're going to get 1 over s plus a. So using these particular two principles, the Laplace transform of exponential j at becomes 1 all over s minus ja. Okay, so we have s minus ja, and minus the Laplace transform of exponential negative jat becomes 1 all over s plus ja. Okay, so you are now going to have 1 over 2j, then into, when you solve this bracket, you're going to get s plus ja minus s minus ja all over you now have s minus ja and s plus ja. Okay, so when you solve this, you're going to get 1 over 2j. Open the bracket in the numerator, you have you just be left with, if you look at it very well, s will cancel out s when you open the bracket. Minus times minus makes this one plus, so ja plus ja gives me 2ja all over. So when you expand complex conjugates, you're going to get what? S square plus a square. Okay, when you expand complex conjugates, it's just like difference of two squares, s minus ja, s plus ja. That is s square minus ja square. Okay, so this is s square minus j square a square, and since j square is equal to minus 1 from complex numbers, s square minus 1 is plus 1, and you now have your a square. So this is how this became this. If you want to do the expansion gradually by yourself, you still arrive at this point. So 2j cancels out 2j, and the Laplace transform of sine at becomes what? A over s square plus a square. Is that okay? So this is for the Laplace transform of sine jat. So similarly, the Laplace transform of cos at can be solved. You can pause the video and do it by yourself, but if you want to practice along with me, it is going to be the Laplace transform of we have exponential jat plus exponential minus jat over 2. Is that okay? So this is 1 over 2 Laplace transform of exponential jat plus exponential minus jat. Okay, so when you solve this Laplace transform, sorry about that, Laplace transform of cos at now becomes 1 over 2. Okay, when we expand this, we're going to get the Laplace transform of exponential jat is 1 over s minus ja, then plus the Laplace transform of exponential negative jat is 1 over s plus ja from our Laplace transform introduction. So when you solve this, you get 1 over 2 open brackets, you have s, okay, plus ja, then plus s minus ja over s minus ja and s plus ja, right? So finally, you have that the Laplace transform of cos at is 1 over 2. So the numerator evaluates to 2s over, you have the denominator evaluating to s square plus a square. So finally 2 cancels out 2, then you now have what? S all over what? S square plus what? A square. So this is the Laplace transform of cos at. So this is just one way of proving that the Laplace transform of cos at and sine at is as I have written above, okay, for trigonometric functions. So in future videos, I'll show you more cooler ways of deriving it, okay, and everything revolves around how good you are with complex numbers. So let's look at 2 more cases that you need to know for Laplace transforms, which is the Laplace transform of hyperbolic functions and the Laplace transforms of derivatives. Then we'll jump into some examples in the next video, and that will be all for Laplace transforms for ordinary differential equations. Pretty cool, right? Okay, so stay tuned. So guys, let's look at the Laplace transform for hyperbolic functions. So looking at hyperbolic functions, we have our sine, okay, sine h. So the Laplace transform of sine h, or we call it shine, S-H-I-N-E, okay, that's how we call it. This Laplace transform of this particular one, okay guys, let's look at the Laplace transform for hyperbolic functions. So our hyperbolic functions are the likes of sine 80 and cos 80 and so on and so forth. So we want to find first of all the Laplace transform for sine 80, and let's see that the Laplace transform for sine 80. Okay, it's actually sine, then you put a h to denote hyperbolic. The h make us pronounce sine h as shine. Okay, you pronounce it as shine. So when you take the Laplace transform of sine 80, you're going to get a over s square minus what? A square, just almost like the one for sine. And the Laplace transform of cos 80 is just like the one for cos. So you have s over s square minus a square. Is that okay? So the only difference is that the denominator is actually having a minus sign, s square minus a square, compared to the one for trigonometric functions where we have plus. Is that okay? So you need to know these forms, and I believe you will be okay. So I want you to be able to prove it by yourself. I'll just give you the expo for sine 80. So sine 80 in exponential form is exponential 80 minus exponential minus 80 all over 2, and cos 80 is the same thing as exponential 80 plus exponential minus 80 over 2. So using the same steps that I used to prove for sine and cos, I want you to follow the same steps and be able to prove that the Laplace transforms for sine 80 and cos 80 are respectively this and this. Now let's go to the final one for this video, which is the Laplace transform for derivatives. So we now have derivatives. So Laplace transform for derivatives. So in this particular case, we are going to be finding the Laplace transform for y, okay, which is the zeroth derivative, the Laplace transform for y prime, which is the first derivative, and the Laplace transform for y prime prime, which is the second derivative, and we are going to generalize, and the Laplace transform for, or let me just say y prime prime prime, which is the third derivative, then the Laplace transform for y raised to the power of n, which is the nth derivative. So I just want you to observe a trend. Now when you find the Laplace transform of y, of course we are assuming that let y be a function of t in this case. So let y be a function of t, because Laplace transform transforms a function from the time domain to the frequency domain. When you take the Laplace transform of y, you're going to get capital letter y of s. Is that okay? Capital letter y of s. If you take the Laplace transform of small letter x, you're going to get capital letter x of s. So when you take the Laplace transform of the first derivative, time will not allow me to prove it here, but I'll prove it in another video in the future. The Laplace transform of y prime is going to be written as the s variable multiplied by y of s, then minus an initial condition, which is y of 0. Okay, minus initial condition, which is y of 0. If you take the Laplace transform of y prime prime, observe how we are going to build on this one. When we build, we'll have s square y of s, then minus, okay, we'll have s, then initial condition y of 0, then minus, we'll now have our y prime of 0. Okay, so this is how it is. This is how it normally happens. Okay, when you're taking Laplace transform, s square y of s minus sy of 0 and minus y prime of 0. So the most important thing is this place. Okay, when you're taking the Laplace transform of the second derivative, the power of s on that particular first term having capital letter y of s will be 2. Now let's look at y prime prime prime. You must have already discovered the pattern here. So when you take the Laplace transform of this one, you're going to get you have s cube y of s. Are you with me? Then minus s square. So we'll start with the first initial condition, which is y of 0. We'll keep going, minus, it's always minus, okay, always minus. Then you now have s you can see that as the initial condition is building up, okay, s is going down. So you now have s y prime of 0. Then when s has a 0 power, then we'll have the last initial condition, which in this case is y prime prime of 0. Is that okay? So this is how to form the Laplace transform of derivatives. And when you want to find the Laplace transform of the nth derivatives, so you will now discover that we are going to have, first of all, s raised to the power of n. So we now have y of s, okay? Then we'll now start going, minus s raised to the power of n minus 1. So we now have y of 0. We'll keep going, minus s raised to the power of n minus 2. So we'll now have y prime of 0. Okay, so can you observe the trend? So minus s raised to the power of n minus 3 will have y prime prime of 0. So we'll keep going, okay? Then we'll now minus again. Let's say we come to the point where we have s raised to the power of 3. So what do you think the power of, or the derivative of y is going to be in that case? Who can guess? Who can guess what the derivative is going to be? Is that okay? So I can easily guess now what the derivative will be. This is the second derivative in this case, right? This place is second derivative, and this particular power is what? This particular power is what? Is n minus 3. Is that okay? So since this power is n minus 3, I want you to observe some similarity between this term and this term. N minus 3 plus 2. I got the 2 from here as the second derivative. Is actually n minus 1. Is that okay? If you repeat the same thing here, you have n minus 2 plus first derivative is 1, and you get n minus 1. So if you repeat the same thing on this particular place, you have n minus 1 plus 0. Y of 0 is the 0th derivative, so you still get n minus 1. So you can see that in each of these terms, the power sums up to n minus 1. Apart from these first terms, every other term must have the property that the power sums up to what? N minus 1. So if I want to generate it for this particular term, s cubed, I'll now have what? Y raised to the power of what? I need something like this, n minus, that's right, 4. Good. Of 0. So that when we add these two, we'll get n minus 1. So 3 plus n minus 4 gives me n minus what? 1. Is that okay? So we'll now have minus s square y, okay? We have n minus 3 of 0. Then we keep building, minus s, and now have what? Y n minus 2 of 0. Then finally we'll now have minus y n minus 1 of 0. So this y n minus 1 of 0, as you can see, is actually correct, because in all the problems that we've been seeing, if we start with the Laplace transform of the first derivative, we are going to end at the initial condition for the 0th derivative. If we start with the Laplace transform of the second derivative, we are going to end with the initial condition for the first derivative. So just one derivative lower in order than where we are starting from. So if we start with the Laplace transform of the third derivative, we are ending with the initial condition for the second derivative. So when we start with the Laplace transform of the nth derivative, the initial condition will be the n minus 1th derivative. So this is the general form for writing the Laplace transform of y raised to the power of n. So when we are solving problems in Laplace transform in the future, we need to know how to write the Laplace transform of derivatives, and I hope you should go through this video very well so that you can understand how to write it. So thank you for watching this video. In the next examples, we are going to look at a couple of examples on how to solve Laplace transform. Of course, okay, Laplace transform requires just two knowledge. Number one is you should know the Laplace transform of the basic forms I've written out here: the polynomials, the exponentials, the trigonometrics, the hyperbolics, then the derivatives. Then secondly, you should know or you should remember partial fractions, okay, to a good extent, and to help you while you're solving problems on Laplace transform. So stay tuned, like, subscribe, share, hit the notification button to stay updated, and look out for the next video in the playlist. Thank you very much and take good care.